Hello everyone, my name is Fen Lu. Today I'm gonna to present this paper called Knowledge Discovery from Imbalanced and Noisy Data. First of all, I'm gonna to do a brief introduction. So building data mining models using unreliable or abnormal data sets presents a significant challenge to classifier construction. Class imbalance and labeling errors present significant challenges to data mining and knowledge discovery applications. So basically, learning from poor quality data will result in suboptimal performance. Also, in recent years, all studies shown that the quality of data are really important. So basically, we have a different kind of learners, and we have different kind of techniques. However, um, however, I think the most important thing, and first of all, we should have the good quality of data. And also, we are facing different dimensions of data qualities. For example, there are data noise, labeling errors, attribute noise, missing values. And also another commonly encountered challenge in data mining applications is the occurrence of class imbalance. So what is class imbalance? Class imbalance, we could define a data set used for a binary classification test is imbalanced if the number of positive examples is unequal or usually typical less than the number of negative examples. Um, a positive example are typically defined as the minority class, while negative examples belong to the majority class. However, class imbalance is not necessarily a data quality issue. It can, it can at times be related. So, for example, when constructing data set for use in data mining analysis, it is common in some application domains for the observation to be given the negative class by default unless some event occurs, in which case the example is labeled as positive. If the recording mechanism is faulty or if human errors is involved in recording the occurrence of the positive class, there may be very few records of the event and hence few examples in the training dataset are labeled as positive. Then at so basically, in the other words, data quality issue may in some situation actually cause the class imbalance, or at least making the problem it's harder. After this, I'm gonna to talk about the motivation why the author doing this huge project. Since this paper is solving a lot of problems, so basically, um, class imbalance is an issue encountered by data mining, by data miners in a wide variety of fields. And the use of sampling technique to improve classification performance has received significant attention in different works. And also in real world data often suffers from data quality issue, especially class noise, without full awareness of the extent of class noise in the data. So they attempt to sample the imbalanced data prior to constructing classification models for the purpose of obtaining an alternate class distribution. So uh, this work provides a significant contributions to the disciplines of data quality and learning from imbalanced data, which is really, I think, in my mind, it's a really huge project, and it shows significant work to to different learners with different data sets with different sampling techniques. But I will introduce later in this paper. We are mainly focused on 11 different types of learner. So now I'm gonna to introduce the data sets. The data sets was made available through the Matrix Data Program at NASA, um, and include software measurement data and associate error data collected at the function or method level. So the software measurement data used for this study are from 5 NASA software projects, um, which are CM1, MW1, PC1, KC1, and KC3. I'm gonna to brief introduce all of them. So for the CM1 project, written in C, is a science instrument system used for mission measurement. The MW1 project, written in C, is the software from a zero gravity experiment related to combustions. The PC-1 project, written in C, is a flight software from Earth orbiting satellite. The KC-1 and KC-3 projects are different components of the same mission project. However, they constitute different personnel and have no software overlap other than minimal third-party software libraries. The KC-1 system, which written in C++, and the KC3 system written in Java. And KC3 is a software developed for collection, processing, and delivery of satellite metadata. Also, there are two other data sets called OptDigit and the nursery. So for the nursery data, which has 8 attributes, contains information for ranking nursery schools. The dataset original contains 5 classes, one of which very recommended was selected in this work to be the positive class. And while the remaining class values were grouped together to form a negative class. And both of them are larger than the 5 software measurement dataset. And also, as mentioned in this paper, the nursery dataset is the most imbalanced of the 7 datasets considered in this work. Also, this dataset provides a wide range of size in balanced level and application domains. Through this, and also the other thing we should know, like all those 7 datasets is a binary class, and the consideration of multi-class domains will be left to the future work. So after introduce the 7 different data sets, now we are gonna to apply data pre-processing for all of them. So approach with in here we are gonna to call the first 5 like software measurement dataset as SE dataset. So in the other word, so the approach with the SE dataset was to first create a subset called DC belong to D. Then for each of the 5 dataset D, such as the target concept in DC is learnable. So in the other word, learners constructed DC should achieve perfect or near perfect classification accuracy. Then once DC is derived, noise injection can be performed relative to this new dataset. In other words, class noise is injected relative to the target concept in DC. So the technical the technique they are going to apply is called RBCM based filter, which is proposed for the same research group. And also, so basically, the numerous classifier were constructed using the filter dataset DEC with few or no misclassified examples. So the SE, which is the first 5 dataset used in our study, have the percentage of the minority examples ranging from 6.43% to 19.78%, and are therefore imbalanced with respect to the class. So we could see the next slides. I provide a table with the dataset characteristics. It shows the characteristics of the original dataset, which in column 2, 3, and 4. And also, I show the transformed in column like a number of positive, number of negative, and number of and the percentage of positive in the column 5, 6, and 7. So also like for the nursery, for this nursery and opt digits data set, since they are unlike the first 5 dataset, cleaning was not undertaken prior to noise injection, so which in our previous experience has shown that these 2 datasets are relatively free from class noise. So basically, we are gonna to ignore those 2 at the first step. Then we are gonna to separate. So the empirical results are presented separately for those 2 datasets. So after the data pre-processing, we are gonna to do the noise injection. At this step, we have the author raised 2 questions. The first question is like how much noise should be injected into the data set. I think for the first question, I think it's really easy since based on the data generation process, data sets from different domains may have like different level of noise. So then there are like second question, what proportions should noise be injection into each class? This question will be harder since it may require some justification. So at this work, they actually consider the impact of varying the class distribution of noise, which has been overlooked in previous studies. So in this experiment, they are going to use lambda and psi to denote different parameters. So for for parameter lambda, they are gonna to use it to denote as level of class noise in the data set. And it will be in 5 different levels, which will be 10%, 20%, 30%, 40%, and 50%. And they also gonna to denote psi from 0 to 100%. And after the data injection, the data n denote as data C after the injection of the class noise. Also, here is the noise simulation details for the KC1 dataset. Since in the simulation, the total number of noise example will be corrupted in each dataset is given by 2 times lambda times SP. Like for example, in KC1 dataset has 271 positive and 1093 negative examples as shown in PPT, and which at the 30% noise level, KC1 will be correct with 2 times 30% times 271, which is 163 instance. So which in this table, we are gonna to show you um, the some result like no as like but first of all we are going to see like as the 100% of positive examples and um, as column 6 and 7 um, as column 6 and 7 and there are 325 positive examples of which around 67 um, 67 60.7% or like 54 are noise. And the last row of the table, which lambda is equal to 50% and psi equal to 100%, resulted in dataset with no positive examples, and hence this will be removed from our experiment. Also, I think I might forgot something. Like in this entire table actually present noise corrupt statistic from KC1 dataset, which is noise injection has 271 positive and 1093 negative examples, and with lambda at 10%. Like for 54 examples are injected with noise. Since KC1 has like I think it's 13, 13, 1364 total examples. 54 noise instance is about like 4%, which is right here like second and third column 54 with 4%. So after corruption of KC1, the percentage of positive examples ranging from 4% to 39.7%. Also, we are gonna to measure like how good the performance is, right? So in this experiment, we are using two different type performance measurement. The first one called area under the ROC curve, which is AUC, and the other one called KS. KS measure is the maximum difference between the cumulate distribution function of the predict probabilities of examples in each class. So in other words, KS measures how far apart the distribution functions are and how well the learner is able to separate positive and negative class examples. Also, I'm gonna to introduce 11 different learners. So here we have K-nearest neighbor, we have SVM, we have naive Bayes, we have random forest, we have C.45 decision trees. All of this, I think we are really familiar. We are really familiar with them, and also all the evaluating will use 10 for the cross validation, which like when we building a learner, 9 folders will be like a training data set, and with the remaining folder acting as a test data set. So In order to show how big the project is, in total for the 5 data set, we are going to for each of them we are going to run 10 times, 10 times of 10 folder cross validation, and which will be like 500. Also for lambda, we have 5 different parameters. For psi, we have different. We also have 5 different parameters. After applying all of them, I think for even for the 5 simple data set, we are gonna to run 2 million times, and that's not even including the UCI data set. So for the experimental result, we have experimental evaluation 1, and for this presentation, I'm only gonna to talk about evaluation 1 um, since I don't have enough time. So the experimental evaluation 1 is like learning from imbalanced and noisy data. So as we can see, this is a this this figure displayed AUC for the different values of lambda and psi for each learner built without using sampling techniques, and averaged over 5 software engineering data sets. So so from this graph, we could see like for lambda at when lambda actually when psi equal to 0, and for all level of noise lambda, the performance of learner is often very similar. And for most of learners, for line and like lambda equal to 10%, is relative like horizontal, means that the AUC does not dramatically decrease. And when lambda increase, the slope of the line becomes steeper as like psi increase for almost all learners. Also, there is a strong inverse correlation between lambda and AUC across psi. As lambda increase, the performance of the learner decrease. Through this impact is more significant with higher value of psi. In additional increase of the percentage of the minority class noise generally decrease classifier performance. Also, here is a performance with different noise level. As we can see, we have 5 SE dataset right here with different noise level and 2 AUC with different noise level. So from this table, we have a lot of stuff to talk about. But since of the time issue, I'm gonna to only talk about like from the table we could see like naive Bayes is the most stable learner of the 11 considered in this study, and however, like 2 newer and more like complex techniques like random forest and SVM are impacted more by class noise than some of the simpler algorithms such naive Bayes and 5 nearest neighbor. Also, like there is something really interesting like for decision tree algorithm, since usually like a Pruitt sigma will help it to build better performance, to build a better tree, have better performance. However, in here it shows the Pruitt sigma actually not really helpful. And also in this also in here it applied ANOVA test. So ANOVA model are useful because the variability in performance can be divided among the different experiment factors, allowing the factor which significantly contribute to change in the performance to be determined. And here it also has a table for the ANOVA result. And we can see all of them are actually less than 5%, I think. Also, here is the SE dataset with the different noise level. Since time is, I'm not going to talk about this. So for the result, in the beginning of this paper, it raised some questions about the effect of class noise in the imbalanced data set uniform across different learning algorithms. Here also point out a really interesting things like the proving sigma actually not really helpful, and also as expected, like five nearest neighbor was generally more robust and performed better than two nearest neighbor. And also like it also point out the newer and the complexer learner actually not performance as well as the simple um, algorithms such as naive Bayes. So any questions? If you have any questions, you could email to my email address is right here, fliu2016@fau.edu. So basically, this is a really good paper. It shows you different learners applied to different data set with different performance, and you can see a really interesting result. And some of them you might not. It's opposite with what you learned from school. And also this is really long paper, it's around 30 pages, so it's really hard to fit all the results in like 25 minutes presentation. I really encourage you to read all these papers and go over all the tables and graphs. I think it's really useful in the real world um, learning for this paper. Yeah, thanks. That's all. Bye.